All right, so today we're going to be discussing surface integrals of vector fields. So in the previous lesson, we talked about surface integrals in general over surfaces. Now we're going to do surface integrals over vector fields. And what we have to first discuss are just the concept of an oriented surface. So an oriented surface is a specific type of surface where that at every point, if you consider a vector, a normal vector coming out at every point, if you move that point, the normal vector will vary. So that's considered an oriented surface. So oriented surface, an example of a non-oriented surface would be a plane, because a plane, the normal vector does not vary. If you move anywhere on a plane, the normal stays the same, whereas if you move on an oriented surface, n varies continuously over that surface. And that normal vector can either orient outwards, the way it is on the picture on the left, or it can orient inwards. So if it is oriented outwards, this is considered on the left positive orientation, and on the right, it's considered, when it goes inwards, negative orientation. And the formula for finding the normals, all of these normals, is given here, where it's the cross product of the parameterization of the surface over the magnitude of that cross product, and that's what makes that normal a unit vector, because you divide it by the magnitude of the cross product. If you're orienting it inward, you have negative orientation. It's just the opposite, because if it's the opposite of n, you're going into the surface instead of out of the surface. So today we're going to be integrating over a vector field. Or taking a surface integral of a vector field. So the surface integral in a vector field is also known as three-dimensional flux. And one of the things that three-dimensional flux measures is how much of fluid flows through a given surface. And so if you have this oriented surface, and what you have to consider is the oriented surface actually has no tension to it. So the surface itself doesn't restrict the flow at all. So consider, for example, like a fishing net, where fluids can flow in and out of it freely. It isn't restricted at all. You can consider how much of fluid flows. That is the flux, and the surface integral of the vector field over that surface is the flux. And that's what this surface integral in a vector field calculates. And so the notation for it is the double integral over the surface S of the vector field F ds, and this is how you calculate it. So notice the calculation involves knowing the vector field there, denoted by the capital F, and it also involves knowing the surface as you have parameterized it in terms of two parameters here listed as U and V, but you know you can choose any two parameters. You'll find R sub U, R sub V, so those are the partial derivatives with respect to U, and then with respect to V, you'll find the cross product of those, and then take the dot product of the vector field and the cross product, and that is your integrand. And you'll take the double integral of that with respect to A, and the bounds are determined by your parameters U and V, much like we did for the surface integrals. So, are we ready to do one? Well, before we hop in, I just want to let you know in terms of the orientation, if they tell you it has a positive orientation, your surface integral result will be positive. If the problem tells you have negative orientation, your surface integral will be negative. So in the end, if you end up with a negative versus a positive integral and it's not kind of the sign that you expected, you can just switch the sign. The reason why you can kind of just make it work is because over here, this particular calculation it's going to be positive or negative depending on what you chose to put first in this cross product. Because RU cross RV equals the opposite of RV cross RU. And that's pretty arbitrary. You know, you choose your parameters, you choose the order in which you take the cross product. So depending on how you decide your parameters and decide to do the order of your cross product, that's going to make this particular quantity positive or negative, which will then change the sign of the dot product here. So in the end, if the signs are not working and they say, hey, you have a positively oriented surface integral over a vector field and your answer is negative, then just take the opposite. So don't overthink it and stress out. It just means that they're intending on you having a positive answer in the end. So that was some frustrations I had when I was doing my work, and I'm like, oh, okay, it's not a big deal. It's okay. All right, so let's first start with calculating flux across a sphere. And our surface is going to be the unit sphere. And our vector field F is going to be given by just Z for the X component, Y for the Y component, and X for the Z component. Because the surface is a sphere, we're going to use spherical coordinates. So the quantity, the parameter that does not change is rho. Rho is 1. So I can set X equal to sine phi cosine theta. I can set Y equal to sine phi sine theta. And I can set Z equal to cosine of phi. And again, those are just our standard definitions using spherical coordinates, setting rho at 1 because we have a unit sphere. Also, because it is the entire sphere and not like a hemisphere or a quarter sphere or them saying it's the first octave, we can set theta between 0 and 2 pi. And phi between 0 and pi. Questions so far? So the first thing I'm going to do is rewrite our vector field in terms of our parameters, because we have to reparameterize the vector field in terms of our parameters phi and theta. So notice our vector field has z, y, x. So I'm going to rewrite our vector field in terms of phi and theta. So it starts with z, and then goes to y, and then goes to x. So that is our vector field parameterized with the parameters we chose, which are spherical coordinates. Then we take the dot product of that with r phi cross r theta. So what we have to do is calculate r phi cross r theta, which is actually kind of a big deal. Now recall that in section 13.6a, we did this. We did this with a hemisphere of radius 2. Please nod if you remember this. In your notes, we did this with a hemisphere of radius 2. It was a pretty long problem, and I said, keep a little like star, a highlight, because you're not going to want to do this again. So what we found was that from that section's notes, our phi cross our theta, and we were actually doing it with a sphere, and it was a hemisphere, you know, like the upper half, but that didn't mattering at this point because we didn't put bounds in. But we were using one of radius 2, so now we're just going to go radius 1. So we'll scale it back a little bit. But this would be the cross product for radius 1. Sine squared phi cosine theta, sine squared phi sine theta, and sine phi cosine phi. And so again, we did this work already. We found r sub phi by doing the partials with respect to phi. We did r sub theta, partials with respect to theta, and then we did the cross product. And in that problem, we then had to find the magnitude of that. Now, we don't have to for surface integrals of a vector field, but we did need the cross product before we found the magnitude, so we had this step. But it was just sphere of radius 2 versus 1. Okay. So now we have that piece of it. We have the vector field. We have the cross product of all of the partials of these two vectors here. Now the integrand is the dot product of the vector field and r phi cross r theta. So remember to do the dot product. It's the x dot the x, the y dot the y, and the, let's do green, the z dot the z, or the z times the z, and then you add up all of those products. All right, so check your products there. And again, careful consideration of what's a phi and what's a theta, because that's very easy to just make a horizontal line, a vertical line there. All right, questions on that dot product? So now it looks as if our yellow highlight and our green highlight are actually the same terms. So we can combine those like terms to get our integrand. And we know our bounds because we kind of started with those. So we have from 0 to 2 pi for our d theta, and our 0 to phi or pi d phi. Questions? Yeah.
For surface integrals, do you not have to like do the like times 4 sine phi thing?
So because you multiply by the dot product of the parameterization here, that accounts for it. Kind of that takes care of what the Jacobian took care of before. Kind of like we had the magnitude of the cross product in just the regular surface integrals, that accounted for the Jacobian. The Jacobian is accounted for right here by taking the dot product with r phi cross r theta. So that's where we account for it there. That's a great question. Other questions? Okay, so a gnarly integral, right? So what we're actually going to do is split this into two double integrals, and then each double integral I'm going to split into the two factors. So let's do that. So by using a property of integration that applies to single, double, triple integrals, you know the sum inside of an integral can be the integral of a sum. So what I did is I separated it and then did a factorization so I could call it two separate integrals. Yep.
Would the third integral be d phi?
Oh yeah, good eye. So what we want to look for is things that will help us out. One thing I've noticed is that is the font getting too small here, the writing? Okay, let me know if it gets too tiny. The integral of cosine is sine theta, and sine theta from 0 to 2 pi is 0 minus 0. So that's 0, and 0 times anything, we don't have to do that first integration. So that just saves me a little time. It wouldn't have been a tough one because I would have a 2u squared du there, but still it's one I don't have to do because 0 times anything is 0. Unfortunately, I don't get that kind of cool thing happening in that next set of integrals. So what I did in the next set of integrals is in your textbook, you have a table of integrals for different powers of sine and cosine. So I used the table to find those integrals. You could also just use your calculator because these are both single integrations. So depending on your level of commitment to your math journey and or how over it you are at any one point, you can use a calculator or a table. That's going to end up being 4/3. This is going to end up being pi. So we get 0 plus 4/3 times pi. So the result is going to be 4 pi over 3. But I just didn't want to do the whatever trig identities or that we would need to do that. All right, questions on that? Okay, so that's flux across a sphere, utilizing the dot or the cross product and the dot product and some ugly integral, some nicer integral. Okay, we're going to do another one. think we might need to do a 2-pager for this one. Let's read the problem first. Evaluate the surface integral for the given vector field in the oriented surface. In other words, find the flux. We're going to find the positive orientation, so we know we want the final answer to be positive. So our surface is the boundary of the region enclosed by the cylinder. X squared plus z squared equals 1. And the planes z or y equals 0 and x plus y equals 2. So it's going to benefit us to have a picture in our heads or in reality of what this looks like. How many surfaces is this? Will this be? Any ideas?
3.
Yes, it is 3. So you have a cylinder, which is our traditional cylinder. You have y equals 0, just a flat plane on the bottom, and then you have the plane x plus y equals 2, which is a slanted plane on the top. So I'm just going to orient this the way my mind thinks of it, even though if you want to consider it oriented like a little bit differently, you can, rotate it. But that's essentially what's happening. We have y equals 0 on the bottom. Y equals 2 minus x on the top, if you want to consider them both in terms of y. And that's your surface. It's almost like, I have my oatmeal container, my overnight oats, and if I just took a machete and kind of sliced it at an angle, that would be the surface. So you have 3 surfaces. You have your cylinder going around, you have the top plane, which is at an angle, and you have the bottom plane, which is flat on the XZ plane. So three surface integrals for the vector field. So that's what makes these problems a little bit longer than we might anticipate. And I really appreciate your attention here. You all are doing a great job. So let's start with one surface. Doesn't matter which one we start with. We're just going to add them all up in the end. And I'm going to do the cylinder. So since it is a cylinder, I'm going to use cylindrical coordinates. So because the action is happening on the YZ plane, or I'm sorry, the XZ plane, I'm going to call X R cosine theta, but we know what R is. R is 1 because you're on the outside. This is just the outside of the cylinder. So X is going to be cosine theta, or 1 cosine theta. Y, I'm just going to have the Y. And Z is going to be 1 sine theta. And then because we're going all the way around the circle, theta is going to go 0 to 2 pi. What are the, it's actually tiny. Can you all read that? Yeah. Okay. What are the limits on Y?
0 to 2 minus x.
Yeah. Y is 0 to 2 minus cosine theta. Because we're orienting everything in terms of our parameters theta and y. So we have y bounded on the bottom by 0 and y bounded on the top by this line or this plane 2 minus x, and x is cosine theta. Questions on that? So the x and z move it around in a circle. So you have this circle that's moved around by x and z, and the y is what makes it a surface. It takes it from 0 all the way to this slanty part. And what makes it slanty is it goes not from 0 to 4, like that would make the cylinder 4 units high. It goes 0 to a slant, and that's what makes it a slant. Questions on that? All right, so now we have to start to write our, let's just rewrite our vector field. So F now, in terms of theta and y, because those are our two parameters, are going to be x, which is cosine theta, y, which is y, and 5. So as I read x, y, 5, x, y, 5, x, y, 5, just reading that off. So that's my vector field now parameterized in terms of our two parameters. Now I need to write our theta and our y. So now I'm taking the derivatives of x, y, and z with respect to theta. So x, y, and z with respect to theta, we get negative sine theta, 0, and cosine theta. Taking the partials of our parameterized surface with respect to theta for our x, y, and z. And then our other parameter was y. So r sub y is nice, it's 0, 1, 0. So we take the partial of x, y, and z with respect to y. And so the first and the last get just obliterated because there's no y's in them, and the derivative of y with respect to y is just 1. We need the cross product for our integrand. So let's do r theta cross r y. And what I like to do is just kind of imagine it instead of rewriting everything. So this is I, J, K. To do that cross product, everyone okay? I don't want to kill your souls, I promise. And what I get with that cross product is negative cosine theta for the I, 0 for the J, and negative sine theta for the K. And now I have to do the dot product of F and that cross product, and that cross product. So I'm doing the dot product of these two for my integrand. Seems like a lot of steps. Okay. So it is the double integral of the dot product of these two. If we look at the formula. So what that's going to be is negative cosine squared theta minus 5 sine theta dy d theta. Really in any order, but I'll just do dy d theta. And then I can factor it since we have no y's. And the y went, oh shoot, I can't. So this I cannot separate out into two single integrals because you can only do that if the bounds are numeric and these bounds are not numeric. So let's take the initial integral with respect to y. There's no y values in this, so what I end up doing is just, this is gonna be y times that quantity, so I'll just end up multiplying my bound 2 minus cosine theta times my integrand. It'll just be y times the integrand, and then I'll fill in the bound, that 2 minus cosine theta. So that'll be my new integrand. And I'll go ahead and multiply all that out. I'll get negative 2 cosine squared theta, negative 10 sine theta, plus cosine cubed theta. Running out of room, let's scooch. Plus 5 sine theta cosine theta. D theta. And this is where it really benefits you to know multiples of pi, because then you put it in your calculator, because there's no way at this point I was going to do this by hand, and I got negative 2 pi. And then I knew we were looking for positive orientation, because if you recall, the direction said positive orientation, so then I just made it positive. So that's the distance, that's the cylinder part. That's the part that wraps around the oatmeal container. So I have the sides, I need the top and the bottom now. All right. Are we ready for the plane? Okay, we're going to do the slanty plane right now. So S2 is going to be the plane x plus y equals 2. So we're going to keep x. We can write y in terms of x. And we're going to keep z, because z can be whatever it wants. We're in space. This is a plane, it's not a line. Z needs to vary in order for this to be a plane. So in terms of our boundaries, we have to consider the fact that our plane, if we look at our drawing here, is cut off by a circle. You know, it's like you have this plane and it's like a round cookie cutter is cutting out the plane. So our boundaries are really x squared plus y squared, x squared plus z squared has to be less than or equal to 1. We're bounded, it's within that. So it's the plane, but over within that circle. So that's going to be our boundary. So let's calculate our vector field in terms of x and z. So we're going to plug x and z as it is defined with these parameters into here. So what we get is x, y, which is now 2 minus x on this plane, and then 5. Then I have to calculate r sub x which is the partials with respect to x. So I get 1, -1, and 0. Then I do partials with respect to my other parameter z, which is 0, 0, 1. And then if I do ijk to do my cross product, I'm just going to get -1, -1, 0. Then I do the dot product of the vector fields and, wanted to highlight, the vector fields and the cross product I just found. So do the dot product of those two and take the integral of that over the circle. Yep.
Isn't it -1, 1?
The J turns negative.
Minus j.
Oh,
Good eye though. You don't want to sign here. So now when I do the dot product, I get the integral of -x, -2 plus x, dx, dz, over x squared plus z squared, filling in the circle less than or equal to 1. So I think we know what we have to do with a region like that. Don't say it. You want to write the circle boundaries? I don't think you want to write that. All right, let's cross out this x here because those cancel. So let's go to RDRD theta. So with this, since we're going now to polar, we do need to RDRD theta because we didn't polarize it to begin with. Wow, polarized. Love that. Is that a real word?
Yeah.
Polarized? Okay. So, it's the double integral, 0 to 1 for r, 0 to 2 pi, -2 r dr d theta. Bounds are easy because it's a unit circle. Looks like I forgot my pi here. 2 pi. I don't have to change my integrand at all because it is just a number, but I do need to do RDRD theta. I don't know why that's a 2. Theta. Okie dokie. So this is going to be 2 pi for the 0 to 2 pi d theta times 0 to 1 -2r dr. So with this one, we get -r squared from 0 to 1. We get -1 times 2 pi, which is -2 pi, which again, we're going to call 2 pi because of the positive orientation. So far, we have 4 pi. Lastly, all we need is the plane on top, z equals 0. We're so close. So let's do surface 3. You can do this. Plane y equals 0.
Z equals 0, 1.
If we go back, recall that we're doing the plane on the bottom. Y equals 0, and the boundaries are x squared plus y squared, and that fills in the surface for that plane. So we have to make x itself y is going to be 0, because that's where we are, and z is going to be itself on the xz plane. So when we fill in our vector field with the parameters x and z, we get x0, 5. R sub x is the derivative with respect to x of all of our x, y, and z parameterized equations. So we get 1, 0, 0. R sub z, our partials with respect to z, we get 0, 0, 1. So when we do the cross product, ijk, we're going to get 0, negative 1, 0. Now, when we dot these in order to get our integrand, we get 0. So the double integral of 0 dx dz is 0. Doesn't matter the bounds. Yes?
If an e-plane is equal to 0, is it always going to equal 0?
I don't know. So what's our answer?
4 pi.
4 pi. So the sum of all of our surface areas. Now, if you want to keep, and let me make this big, if you don't want to reparameterize and you want to keep your parameters in terms of x and y, and you don't want to reparameterize in terms of like what we've been doing, you can just do that. And we had a similar situation with regular surface integrals, not surface integrals on vector fields. So if your vector field, which we always write it, is written in terms of functions p, q, and r, we don't have to go through this whole process of doing the cross product, finding the partials. Well, we do have to find partials, but we don't have to do the whole cross product. We can just use this formula if you decide to just keep your parameters x and y, and this is how you can calculate the surface integral over a vector field f. So you'll create a function g of x, y, so essentially just solve for z, and then you have your vector field, and then that is how you do your surface integral. Okay? Questions on that?